Let's move to the zonal circulation. So the idea of 10 to the 6 meter scales that Charney was looking for in terms of convective perturbations, and then he said maybe they are being triggered by extratropical perturbations, or the local convections are weakening the stratification, without saying where that convection would come from. So to deal with that conundrum, we had gone through the weak temperature gradient assumption, which simplified the thermodynamic equation in the third chapter. You can go back and revise it. Basically, we said if the diabatic heating can be balanced by vertical adiabatic heating and cooling terms, then we could actually allow baroclinic processes at the 10 to the 6 meter scale. So we had written that static stability vertical advection as n squared over g being approximately balanced by the diabatic heating term. So within the deep tropics, where we know that F goes to 0, so you have to be careful, but we talked about how this meridional scale is important, and the R being large also meant that the scale of the perturbation has to be very large as well to deal with the thumb rules we used before about what happens when the forcing is less than Rossby radius and greater than Rossby radius, and so on. So we were looking at the I hope I'm on the right chapter. Extratropics, where the system is divergent and you have small f and there is a background flow with Rossby radius being less than 1, and you have spatial scales of 10 to the 6 meters. In the tropics at 10 to the 6 meters, you have much smaller f tending towards 0 for the same scale. If you have non-divergent flow, then there is no communication between the lower level and the upper level. So this is the schematic representation of the degree of vertical coupling for dynamic modes of different scales in the tropics and extratropics. We are looking at extratropics here, tropics with 10 to the 6 meter length scale, and tropics with 10 to the 7 meter length scale, right? So the vertical arrows here denote vertical velocity and degree of communication between the lower and upper troposphere in terms of divergence. Okay, so in the tropics at this scale, Rossby radius is not much smaller than 1, because the vertical motions are very rapid and the assumptions we make for small Rossby number don't necessarily hold, which makes it a barotropic system. Whereas at larger scale, the Walker-Cell scales, you have R0 less than 1, and you have divergent flow, and you have vertical communication as shown here. Okay, I don't know why I put that back in there. So we can then think of simple models of zonal circulation. Consider a background state, basic state we have already considered in the two-layer model that I'll show in a minute, which had a meridional shear and a vertical shear. So it was zonally uniform. And we had put a heating term, diabatic heating term, which was a function of latitude and longitude, as we had seen here, the spatial distribution of forcing at day 5, and it had a temporal decay scale, so it ramps up in terms of forcing amplitude and then dies away over days, like this. In the basic state being at rest, we had seen that there was a fast-moving Kelvin wave going eastward and slow-moving Rossby waves going westward. We're going to see the same solution now in the background state given by this. So this was the model we were using, which is described in Appendix J. You had 2 layers in the vertical, upper layer with U1 and basic state U1, U bar 1, sorry, basic state geopotential of phi bar 1, and then perturbation velocities and potentials, and the same at the lower level, and we are looking at this section of the sphere. So there is the upper level wind, which has strong westerlies in the subtropics with weak easterlies in the tropics, and the lower level has weak westerlies and stronger easterlies. And we had looked at the impact of the perturbation kinetic energy, and we were looking for extratropical impact on the tropics, and we had noticed that the perturbation kinetic energy doesn't quite make it into the tropics in this case, but that's a different question. So looking at imposing the heating again in the deep tropics, given here in these colors, similar to the one we had done before in terms of experiments, but now the basic state is not stationary anymore. So you have strong meridional shear and vertical shear. You can see in the vertical also the easterlies and the westerlies are different. So you have easterly shear and westerly shear. And look at the response with forcing at the equator at 250 hectopascal. Let's first look at the surface. So near surface, you expect that the heating is going to have convergence, as we saw before. The heating is going to create lighter air, vertical motions, strongest at the maximum heating. So the geopotential response is shown here as well in contours. Okay. Westerlies on the western side of the heating, easterlies on the eastern side. You can see the asymmetry, and we had talked about the divergence on either side. But in the upper level, you can see that you also induce these off-equatorial cyclones, which obviously are related to the vortex stretching associated with this vertical motion that we talked about, so that the absolute vorticity is changed, and this requires the parcel to move off the equator into Coriolis force, Coriolis or planetary vorticity being non-zero, and adjust the total vorticity to create this off-equatorial cyclones. Okay, so you have still the eastward propagating Kelvin waves and westward propagating Rossby waves, but now we are looking at large scale 10 to the 7 scale motion in the basic state that is not zero, and of course the influence is going to stretch into the subtropics all the way to the poles from this tropical heating. Okay, so in the upper atmosphere the Rossby wave response is clearer, and the weaker opposite side of circulation is seen at the lower level. So as you remember, there's convergence in the lower level, divergence in the upper level. So you can see here easterlies and westerlies diverging away from the heat source in the upper level, with corresponding opposite signed cyclone anticyclone pair at the lower level and the upper level. So this divergent large scale flow is baroclinic, and we don't need the restrictions of the weak temperature gradient here. And the interesting thing is that even if you put the heating at in the subtropics, which corresponds to the monsoon circulation, of course, like the East Asian monsoon and the Indian monsoon, the influence on the equator is still very clear. So obviously there is this meridional communication happening even if the heat source is off the equator in the subtropics. So this is the nature of the zonal circulation, which is affected by the heating that we have talked about in the deep tropics that create large-scale divergent flows and baroclinic processes, and the vortex stretching associated with the diabatic heating and the meridional motion, which also is happening when the heating is off the equator in the monsoonal regions. So that's a very quick explanation of the Walker cell in the context, in the background of what we already learned. And the waves involved here are still the same equatorial Rossby waves and Kelvin waves, and the eastward-westward inertial gravity waves, mixed Rossby gravity waves, and so on, except that we have to remember that the basic state is not zero, so you're going to have these Doppler shifting and the accumulation of energy and stationary states being produced by wave mean flow interactions. So the Walker cell, which has the fixed centers of heating which are only seasonally moving and interannually moving, can be thought of in this wave Doppler shifted stationary wave kind of framework, given the basic state. Okay, so basic state is explained by the other theories we have looked at in terms of the Hadley cell, eddy fluxes, etc., etc., and now we are looking on top of that this large scale 10 to the 7 scale baroclinic processes and the large scale zonal circulation. Okay, that's the nature of the zonal circulation in a very brief kind of setting. Okay.